So question 7 is quite similar to question 3. The main difference is this time we're being asked about a acid-catalyzed reaction as opposed to a self-catalyzed one. So for the first part of this question, we're simply asked to write down the integrated rate equation for an acid-catalyzed step growth polymerization. So this is simply C0 K prime, that's small k, T equals 1 over 1 minus P, and that is minus 1. And in this, CO is the initial monomer concentration again. K prime is the rate constant. T is the time of the reaction, again in seconds. And P is the extent of reaction. So the units for this, again, moles per decimeter cubed, very standard for any concentration you're dealing with. Rate constant, we'll get on to that in a second, we'll have to work it out again properly like last time. Time, seconds, as I said earlier, and extent of reaction has no units. So if for the units of K prime, we do what we did last time, we make K prime the subject of this, so K prime equals 1 over 1 minus P minus 1, all in brackets, and this is over CO T. And if we put the units of each constituent into the variables, we get, I'll try and do it here, we get 1 at the top again, because there are no units of P and no other variables, and then for C0 we have moles per decimeter cubed, and then for time we have seconds. So again, when you have powers underneath a 1 or at the bottom of any fraction, when you're moving it to the top, all you have to do is reverse the sign of each power. So if we view moles and seconds as being just to the power of 1 here, we then get moles to the minus 1, decimeters to the minus 3, decimeters to the 3, and then seconds to the minus 1. And that is our unit for K prime. So the next part of this question is asking us to draw a graph to confirm that the reaction is acid catalyzed. So for this, very similar to what we did last time, we are doing a plot of 1 over 1 minus P, not squared this time, just from this equation. We're doing that versus time, and if that is linear, then the reaction is acid catalyzed. So if we just draw a new table, so we have time in minutes, extent of reaction P, and then 1 over 1 minus P. We have 0, 40, 80, and 120. And for P, again I'm just copying this down from the question, 0.879, 0.935, and 0.956. For 1 over 1 minus P, you're just putting this into your calculator. So this gives us 8.2645, 15.3846, and 22.7273. Just to be clear, you're just putting these values of P into this part of the equation here, you're repeating that. So you just want to do that on a calculator. If you have a Casio scientific calculator, it's quite easy because you have the fraction feature, which is here. That makes it much easier. So you're now trying to plot on a standard graph where the y value is 1 over 1 minus p and the x value is just t. So your graph should look something like this, and the fact that it is linear confirms that it is acid catalyzed. So you want to just write a statement to that effect. So part 3 of this question, I'm going to start over here. First of all, it demands that we recognize that the integrated rate equation, this CO prime kt equals 1 over 1 minus p minus 1, this is in a Cartesian form. And when we say Cartesian, we just mean a standard line on a graph where y equals mx plus c, where y is our y coordinate, obviously, x is our x coordinate, m is the gradient, and then c is the point at which the line crosses the y-axis. Yeah, so y-intercept. So if we rewrite this in a more suitable form, all I'm doing is I'm adding 1 to both sides, so I'm eliminating this 1 and putting it on this side. So we have 1 over 1 minus p equals CO prime k t plus 1. So if we look and compare these two equations, we know from what we just drew the graph that our 1 over 1 minus p was our y, and we also know that the t is the x. So if this is our y, I'll draw something different colour to make it slightly more visible. This is our y, this is our x, the t, and the 1 therefore is the c, the point at which it crosses the y-axis, and then our gradient will be equal to CO prime k. Sorry, it's CO k prime, that's my bad. K prime. So if we consider what the gradient actually is, to work out the gradient for any line, let's say this is a very rough drawing of the graph you should have drawn in neat. To work out the gradient, it's for any point. The gradient of that slope will be the change in y here divided by the change in x. So if we were to calculate the calculate a numerical value for this gradient, we would be able to equilibrate it to CO k prime. So essentially what I'm saying is our gradient is equal to CO k prime. So if we substitute some values of y and x in, so if we take, for instance, these values here, 1 over 1 minus p is 15.3846 and t is equal to 80. So for this, we have the change in y over change in x, as we just said. I'm just going to write it as delta y and delta x. The change in x from 0 to 80, let's say, is simply 80. So at the bottom of this fraction we will have 80, and at the top, change in y, it's not from 0 to 15. Let's draw 15 on here. Sorry, 3846. It's actually 1, because you see that it's crossed the y-axis at 1. So Therefore we have that 15.3846 minus 1, so 14.3846 divided by 80, which gives our gradient equal to 0.1823. So question C is asking us to not work out just the gradient, obviously it's asking us to work out K prime, the rate constant. So if we basically do what we just said, where if this is our gradient, we do that equal to 0.1823, we can work out K prime from this. So we input the initial monomer concentration, which in the question is said to be 0.7 molars. So we put that into here, 0.7 K prime will be equal to 0.1823. So K prime therefore is equal to 0.1823 all over 0.7, which gives a K prime value of 0.2604 moles to the minus 1 decimeter cubed. And then take into account that this value, this 80 we used here, this is minutes, so our unit is minutes to the minus 1, which is undesirable, we want it in seconds. So to go on from here, which is a necessary part, you have to do this, just divide this value by 60, as everyone knows there are 60 seconds in a minute. So for the actual unit, 0.2604 divided by 60, and that is equal to 4.34 times 10 to the minus 3 moles to the minus 1 decimeter cubed per second, and that is your final answer.